It's a pleasure to have Matt Muckley, who is a research engineer at Facebook AI Research Fair. He completed his PhD on MRI acceleration in 2016 from Michigan. And he spent 3.5 years at NYU School of Medicine, working on X-ray, computational tomography, and MRI reconstruction. And since February 2020, he has been at FAIR, where he works on fastMRI. So he'll be telling us about the exciting work that has been happening there. So Matt, you have the floor.
Thank you so much. Okay. Yeah, so first of all, thank you very much for inviting me. I'm very happy to be presenting. Hold on just a sec. Yeah, so the topic of my presentation is evaluating AI-based MR image reconstruction models and some lessons we got from the fastMRI project. So first of all, I want to highlight that fastMRI project is a collaboration between Facebook AI Research and the NYU School of Medicine. So there have been a lot of people that have worked on this project. I'm just listing about 30 here, but there are more than I can list on this one slide. And so I'm presenting a lot of this team's work on behalf of them. I just want to highlight all the efforts of this team over the last few years. And so here's the agenda of my talk. So first of all, I'm going to start by just describing what is the fastMRI project, what were our goals, and then I'm going to go into 3 different subcomponents of the collaboration. The first one is our work towards a 5-minute knee scan. The second one is our work on open competitions with the fastMRI challenges. And the third one is some ongoing work on estimating metrics with undersampled data. And as you can guess from my talk, the common theme that I'm going to try and highlight through all 3 of these is how do we evaluate deep learning based image reconstruction models. So first of all, MRI, magnetic resonance imaging. So I just want to talk a little bit about what it actually is. So on the left here, I'm showing a picture of an MRI scanner. And the way it works is you have a patient who is on this table here. And this patient goes inside this big tube that is shown here. And what's inside the tube is essentially a bunch of superconducting wires. And these superconducting wires create a very large magnetic field in the center of the bore. And what we can do is we can play very specific sequences of electromagnetic pulses and RF pulses to collect data from that allow us to figure out whatever is inside the scanner. And the interesting thing is that the signal that we collect is very sensitive to proton nuclei, which mostly occur in water. So the main part of the body where you have water, of course, is soft tissue. And this property makes MRI very sensitive to soft tissue contrast. So as a result, using MRIs, we can make these beautiful images of soft tissue features like in the brain, the interior of the knee, artery vessels, and we can also image functional aspects of the body and lots of other really cool things. The issue with MRI scans is that they're kind of slow. So they're arguably the best at looking at soft tissue pathology, but they're slow. Oftentimes an MRI session will take 20 minutes to an hour. And this slowness is a big factor that hinders it from wider adoption in the medical imaging community, especially compared to X-ray, CT, and ultrasound. So to basically increase the usability of this particular technology, we would like to shorten the time of an MRI scan. And the reason MRI scans take a long time is because of the way that they acquire the data and reconstruct. So what happens is the patient goes into the scanner, and then we apply a very specific sequence of electromagnetic pulses. And then after applying all these pulses, we can collect one data point of the Fourier transform of whatever is inside the scanner. And then what we can do is we can apply a different, very specific sequence of electromagnetic pulses, and we can collect a different data point of the Fourier transform of whatever's inside the scanner. And so the way MRI works is we do this over and over again, applying lots of different electromagnetic pulses to fill up the entire Fourier transform. And then we can apply the inverse Fourier transform and get the picture. And the issue is that because all of these electromagnetic pulses are different, they all have physical constraints in terms of how much you can ramp up and ramp down the wires in the scanner. And that you can also cause things like peripheral nerve stimulation if you go too fast. And the overall result is we fill up this Fourier transform as fast as possible already. So the only way to reduce the amount of time for a scan is to collect less data. And the issue with collecting less data, if you're familiar with sampling theory, is that you get aliasing. So on the top, I'm showing an example of a fully sampled Fourier transform. You apply an inverse Fourier transform and you get a good image. On the bottom, we subsample and then we get aliasing. So if you're familiar with sampling theory, normally we think of sampling in the time domain, aliasing in the frequency domain, and MRI, because we sample in the frequency domain, we get alias in the spatial domain. Now, there are a few ways to compensate for this. So the big one that's most common is to use parallel imaging. So parallel imaging is where you have several different receive channels around the patient when they're in the scanner. And the interesting thing is for each receive channel, it's only sensitive to the most local region close to it. And you can use these sensitivity patterns to undo the aliasing artifacts that I showed on this slide. Now, the problem is if you're doing 2D imaging, there's like kind of a limitation of taking this past about 2x acceleration. So, and the main thing is like due to numerical instabilities, it's kind of hard to get this to be robust if you do any more than 2x acceleration. So as a result, even with parallel imaging, for 2D imaging, we can't really go past 2x. And so the goal of the fastMRI project is essentially to take what we can get from parallel imaging, which is about 2x acceleration, and pump it up higher, maybe to 4x using AI-based reconstruction methods. And with this goals, we launched the fastMRI project. And so the overall collaboration covered several different areas. Probably the most famous in the community is the release of the fastMRI dataset. So the fastMRI dataset is about a 5.2 terabyte dataset of raw case-based data. And it has two subcomponents. One is the knee data, another one is the brain data. Each one of these is about 2.5, 2.7 terabytes after you decompress them on your hard drive. Also associated with each one are 10,000 DICOM cases. And so this is, to my knowledge, still the largest raw case-based data set in the MRI community. Another thing that we did following on the data set release is we did the reconstruction challenges. So we had a knee reconstruction challenge in 2019 and a brain reconstruction challenge in 2020. We've done work on AI-based reconstruction models. So one example is the end-to-end variational network in GrappaNet. We've worked on post-processing analysis. So one would be like a banding removal that arises to the asymmetric sampling pattern in 2D imaging. We've worked on studying interchangeability for clinical applications, error estimation. We've also done a little bit of work on acquisition in terms of how to sample the case base to be optimal for AI reconstruction. Now, of course, I can't talk about all of this today, so I'm only going to be talking about these topics, the interchangeability study, fastMRI challenges, and a little bit on error estimation. So yeah, I'll go ahead and get started on that topic. So first, I'm going to start with the 5-minute knee scan. So I think the main goal of our project was really oriented around this topic right here. So I think internally, we kind of feel like this is maybe what was our main targeted research contribution for the community. So I'm going to spend quite a bit of time on this. But the history of knee imaging actually goes quite a bit back beyond fastMRI at NYU. So the head of radiology at NYU, Dr. Recht, is a musculoskeletal radiologist by training. So he spends a lot of time on these. And he's kind of made it a goal of the department to get to a 5-minute knee scan going back, about 8 to 10 years. And there have been many researchers at NYU that have worked on this project over the years, trying lots of different approaches, like looking into compressed sensing, simultaneous multi-slice acquisition approaches. And here I'm showing like just one example of a RSNA abstract all the way back from 2014. And the thing is, none of these really quite got all the way there. Compressed sensing was, they developed some really good methods, but the issue was that knee radiologists are very sensitive to the image properties and the contrast in the image. And one requirement of compressed sensing is that you typically have to do a little bit of random sampling. So you can look over here for like a 2D scan. So you might randomly sample this Fourier space. And the issue is that for the spin echo imaging that we do in MRI, there's actually a time dependency to the order you acquire these samples. So if you acquire these samples in a different order, then you will alter the contrast of the final image. And this altering of the contrast was very disruptive to how the radiologists interpreted the images. And as a result, compressed sensing was rejected for clinical practice. So to finally get over the hump, NYU reached out to some researchers at FAIR, and we spun up the fastMRI project. So the collaboration started in January 28th.
Can I interrupt you? I want to know more about this. Yeah. So this is so they actually this was just using total variational L1 regularization, and they actually tried it for this particular types of scans, and they rejected it. So this is not. But is it used in other cases for MRI?
I think John might know more than me, but yeah. So we've at NYU, we do use compressed sensing. The main way we use compressed sensing is with a different technique called GRASP, and it's a dynamic acquisition. And for that, we use a temporal total variation, and that works extremely well. So that was rolled out clinically at NYU and is the basis. I think it's used in a huge fraction of abdominal scans now for motion robustness. So yeah, we got a win with compressed sensing for abdominal imaging, but we weren't able to get a win for knee imaging. Okay, great to know. Thank you. So yeah, so the collaboration kicked off in January 2018, and everyone was really excited. We shared data by summer 2018, and the early days were like pretty fun. So basically saw like, you know, all the things you would expect from the computer vision community, like units, cascaded models, VAEs, GANs. We were the only ones that had the data set at the time, so we broke our own SSIM records on it all the time. But in the end, we didn't actually use any of these models. And I guess the assertion that I'm kind of going to make today is that part of the reason was, at least in this time period, we weren't necessarily looking at the reconstructions the right way. So we were looking at metrics, and we also looked at images. But when we looked at images, we kind of looked at them in the way that you might think of as a data scientist, I say. So I'm picking on this particular paper from StyleGAN. But you know, the way a lot of times when we're thinking about data, you kind of want to think in terms of distributions. So you want to see like the average example, you want to see what happens at the tails, you want to see a wide spread of different cases. So just when you're displaying the images for yourself, a lot of times you'll tile them. And a lot of the presentations we did at this time, we would tile a whole bunch of knee scans and kind of get an overall broad feel for if the models were getting better. And this is a good way to see overall data, but the issue is it's not really how a radiologist looks at a scan. So to look at how a radiologist looks at a scan, what they do is they might take like one image and they zoom in on a tiny itty bitty area of it. So in this case, I'm focusing on this part of the knee. And then they look right here and they say, oh, there's a subchondral osteophyte right there. So you know, it's like really zooming in on a tiny bitty area of one image. And if you're looking at a whole bunch of images and over a wide distribution, it's kind of hard to notice these subtle features. And this is very particular for knee radiology because they have lots of features on this scale they have to look at. So in order to adjust for this, we changed how we were evaluating our models internally, and we moved to a weekly radiologist meeting. So like every single week, we would sit down with a knee radiologist with the latest model we had developed, and the radiologist would go through them and basically say what was there, what was missing. And I think it was a little disheartening at first because a lot of the models, we had better models on the unit, but they were still over smooth. So we would show these models, we make improvements every week, they'd be a little bit sharper, but every single time the knee radiologist would be like, hey, we're losing all these textures in here. I won't be able to find a subchondral osteophyte with this type of model. And a lot of times they wouldn't even look in the pathology region. They would always be looking in kind of these background textures when they notice the smoothing. But the lack of these textures and in these areas up here gave them very low confidence that we would be able to recover the pathologies in the key area around the meniscus. So after getting this signal, we started to turn to new approaches. So the main approach that we looked into was to basically like find ways to incorporate MRI domain expertise with like parallel imaging. And the interesting thing is there had already been MRI work at NYU for deep learning on incorporating parallel imaging before the collaboration. So the main product of this era of work was this model called a variational network. And it's very intuitive to a person from the inverse problems background. So just at a high level, what it is if you can imagine like a cost function when you have a data fidelity term and a regularizer, and then you do gradient descent on that, and you unroll those gradient descent iterations, then what you'll have is you'll have this term that I wrote, that I have on the top here, which is a data fidelity term. So this is A transpose A times U is the image in this case, and F is the data. And then down here, you would have your regularizer gradient. And what the variational network does is it replaces this regularizer component with a neural network. And the neural network has learned convolution weights, learned activations, and these are all pulled together and summed back together and put back into the model. And you just have several iterations of this. And so when some researchers at NYU debuted this algorithm, and I think at ISMRM in 2016, the results were very impressive compared to compressed sensing. So after we had our radiologist review sessions, the team started to look into more of these models that included parallel imaging. And in particular, we spent a lot of time on the variational network and kind of expanded and made it a lot bigger. So, so aside from making it bigger, we replaced the convolutional components with units, and they also added a new component to estimate the sensitivity maps that arise from the MRI physics. And that's because of this sensitivity map estimation component, they called it the end-to-end variational network for accelerated MRI reconstruction. So we adopted this model, and this became the workhorse of our group. And the improvements over like unit were pretty substantial. So here's, going back here, I'm showing a unit example. And by the way, I just want to point out, this is a pretty big unit. So if you run this unit on fastMRI, it will fill up a 32 gigabyte GPU. And even still, this is like the image you get from it, and the variational network of similar capacity gives a much better image. So now you can kind of see we're getting a lot of those textures back. And you know, I think most people can pretty clearly tell this image is quite a bit better than what we were having before. Now, even still, even though our image quality was going up quite a bit, we would still go to our radiologist review sessions, and they would still reject these images because they're very sensitive to like anything, fine features, anything at all. And actually, even you, like if you look at this image, if you kind of look in this dark region, you can still kind of see the smoothing property compared to ground truth. I mean, you can tell that it's not exactly IID down here, and it gets worse at lower field strengths when there's a little bit more denoising that the network naturally does. And so this was another blocker for a little bit. And to get past this point, what we kind of started to do is we looked a little bit into human perception. So the standard thing in computer vision now is we have lots of AI models for doing human perception, like I don't know, there are FID metrics, there are adversarial models, there are all sorts of great things. But because we were MRI people, we were a little more traditional, so we actually looked back in time for human perception studies. And in particular, one presentation that happened previously in the MRI community was this one at the ISMRM Data Sampling and Image Reconstruction Workshop of 2013. So I remember this presentation because this is what kind of opened my eyes to human perception. And it was by Richard Amann. And it was about a half hour, and the title was What a Radiologist Sees. And so at this time, the big topic was compressed sensing. So he was showing lots of compressed sensing examples and basically saying, you know, you have to take into account the human visual system when you present an image, because, you know, we process things in lots of weird ways. And so just to give a feel for like the way the human visual system processes data, he had lots of cases that were, for lack of a better word, I would kind of call them magic tricks, you know, things that you can play on yourself with like a Jupyter notebook. So I have a few of them here just to kind of convince you that your visual system is processing data in strange ways. So this is one magic trick that a lot of people know. So you might see, this is an image that the left side is dark and the right side is bright. And if you look about right here, you might see something that kind of looks like a bright white line. And I can tell you, because I created this image, that line doesn't exist. That's your eyes processing the image and doing a high pass filter at that point. And that's it's just like one well-known property of how we look at things. So here's like another magic trick. So I could ask you the question, okay, which one of these two circles is brighter or darker? And you might say, oh, this one looks like it's darker. And I can tell you, because I generated the image, these two are the exact same color. Your eyes are processing them in slightly different ways because of the background. And another result that a few papers have had, but I don't think there's a very great consensus on why it works, is how we process noise. So here's an example of a very low contrast feature. And if you add a little bit of noise to it, you might see it a little bit better. It's basically several vertical bars. For me, I find this maybe the most incredible one to believe, but there are several papers that say if you add noise to the bars, then you can see them a little bit better at a higher detection rate. So we said we would try that. So we looked into basically dithering the images. And the interesting thing is, like, once we started dithering the reconstructed images with a signal adaptive noise addition, the radiologists couldn't tell the difference anymore. And so so this is a figure that Larry Zitnick created. I switched it up a little bit. So I can give you all about 30 seconds. So I can tell you one of these images is the ground truth. One of these images is the neural network reconstruction, and one of these is neural network reconstruction plus noise. So I'll just wait about 30 seconds for everyone to decide which one is which.
We don't have many radiologists here. Very few. In my paper, I was telling them they all look the same to me, but I don't know. Let's see what people will say.
Yeah, so I've shown this to some non-radiologists. I think you can get the neural network reconstruction one. So the neural network is, I think, on the left. Ground truth is in the middle, and neural network plus noise is on the right. So, so that's the answer. And you can, you can look around right here. You can tell this area is kind of smooth. You can look about right here. You can tell that's a little extra smooth. So you can kind of see this a little bit, and the radiologist is like very sensitive to this. But when we started adding noise, they couldn't tell the difference anymore. In fact, they started liking neural network with noise more than ground truth.
Hey, Matt, could you quickly go back to the bars experiment before and after noise just for a second?
Yeah, so this one, I looked at this and I don't know if I believe it myself. So I did the experiment just to try and play around with it, but
The other thing
is
Zoom may also distort when you add noise. Zoom may change the way the noise is transmitted, may add some JPEG artifacts on top. So, we should better do this with the actual images or the actual slides. Yeah.
Yeah, I can share these slides later.
Yeah, I have a question about the dithering. So at high SNR, it's not going to make a difference, right? So if a radiologist looks at a high SNR image, like a brain image, where there's less noise, you probably don't see the difference. Is this also a result of training on real data that is just noisy? And so, the network is never going to get the noise component quite correct on a sample by sample basis. But if it were truly high SNR imaging, you wouldn't want to add noise back, right?
Yeah, I think that makes sense to me. These were only 3T images, and our target, as you know, is like always square root sum of squares, which is a little noisy. So that could be promoting the network to over smooth a little bit. I could believe that. I don't have any evidence either way.
And then another question I have is, if you're after the reconstruction, if you're putting back the original samples into it, or are you just using the output of the recon? So that's something that we used to do, clinically as well, because our radiologist also said that, but instead of adding noise, we would just add the original measurements, which intrinsically are noisy.
Yeah, that's a great idea. The issue for us is the final reconstruction is kind of disconnected from a systems point of view from the case-based data because it's magnitude.
Right.
So yeah, we don't train in any way for the phase. So there's not a clear way of like reintroducing it.
Yeah.
Also, Konstantin, you have a question?
I've got a question. So I can understand what the radiologist feedback you get. Is it what we might call reference blind? So are you just showing them something and they're saying, oh, I like this, I don't like it? Or are you saying, this is ground truth, which do you prefer more? Because I could imagine, especially when you said that they ended up liking neural network plus noise, that actually worries me, because you're basically, you could imagine faking a particular texture that they've just been accustomed to learning, and then they end up thinking that this is actually a signal of reliability, whereas really it's just random noise. And in contrast, we could imagine that we retrain the radiologists to do reliable diagnosis from neural network produced
Yeah.
images rather than whatever their training is. So
Yeah, I agree. I think that was kind of what we talked about a lot. And I think what people told us was it's too expensive to retrain radiologists.
of course, yeah.
So,
But I mean, so were
we,
you showing them the ground truth for them to say, okay, I see this in the ground truth that I would have missed in your image, or are they just like, this is what, this should look, it feels like this is what it should look like. And so confidence in the upper region, even though that's not where the pathology manifests itself, is a proxy for me to have confidence in the kind of critical regions where I'm looking for something or absence of that something.
yeah, so the real way we address this is we went on to the interchangeability study, which was the last thing I'll talk about here. So basically we got a large number of patients with pathology, and we randomly interspersed neural network reconstructions with the actual clinical standard, and we tested whether the diagnosis changed above the noise level.
Of course, that makes sense.
Yeah.
Thank you.
So yeah, that's the next slide. So after this, we had the confidence to actually try this. We went on to an interchangeability study. We looked at 4x faster knee scans versus 2x parallel imaging. Did this in 108 patients. The 108 patients were reviewed by 6 radiologists. I think each radiologist would look at images like multiple times. And the real test that we were doing is the rate of agreement altered by the use of accelerated sequence.
Matt, I have a quick question.
Yeah, go
On
ahead.
this slide, is the comparison to a 4x prospective scan, or are you taking the 2x and retrospectively downsampling it to 4x?
So all the data was 2x scrappa, and for neural network, we would throw away half of the outer lines. So the actual 4x is about 3.8, and the actual 2x is about 1.9 or whatever. All the real numbers and calculations are in the paper.
So won't that also have an impact on the contrast change, like you were saying before? I mean, if it were truly 4x acquired?
Yes, and we got an NIH grant to study that, and now there's like a prospective knee scan study that Florian and Patricia were working on. Unfortunately, I don't know the status of that study right now. Yeah.
Awesome.
Yeah, and so the conclusion of this study, which I think was maybe the peak of the research work, was we did find that they were diagnostically interchangeable. So we're specifically, if you wanted the exact claim in the paper, the data provide 95% confidence that interchanging the sequences would decrease the likelihood of reader agreement by no more than 4%. So generally the radiologists could not distinguish between which ones were produced by AI, and they actually preferred the AI images in quality versus the traditional scans. So, and this is in this paper in American Journal of Röntgen Genealogy. Yeah, that's it for the interchangeability study. Does anyone have any other questions on this before I move on to the challenges?
Well, I mean, so it's not quite rolled out. I mean, are they using it prospectively at all and kind of evaluating how it is since then?
Yeah, so there is a prospective study I mentioned. And there's also been a lot of work on a multi-site study. I think NYU collaborating with several different hospitals, major research centers that are Siemens partners, maybe. And again, I'm sorry, I'm not part of that study, so I can't. Also, it's ongoing, so I can't give any results on that. But that would, if those studies go through, that will provide a better evidence that this is working.
But would you say that Dr. Recht would say that the 5-minute challenge is solved?
Oh, I think he would really like for it to be solved. Yeah. Yeah, I don't know. I think you have to ask him that. But yeah, he was pretty happy with this result. I'll say that.
And so is the 4x 5 minutes?
Yeah, it's so the nominal scan time is like barely less than 5 minutes. If you take into account table time, it's more than 5 minutes still. Yeah, so that's why we tried really hard to do 6x, but we just couldn't do it.
But just to make it clear, 5 minutes is not a single scan 4x. It's the whole protocol of multiple scans.
Yeah, it's a whole protocol. Yeah.
And what goes wrong with 6X?
What goes wrong with 6X? So what killed 6X was I would say like kind of point spread function effects. So basically like you're fully sampled along X and you're not fully sampled along the other direction. And when you really push the models, you kind of get like some weird texture effects that are anisotropic. And so this I think these are, and we had a hard time getting rid of these effects. It really lowered diagnostic confidence. It was really bad in the fat saturated scans and really bad at 1.5T. Actually, even with 4X, we had some difficulty at 1.5T. Aaron DeFazio developed a generative adversarial network-based method for like kind of correcting the anisotropic patterns. But I think there wasn't high confidence because maybe it was a GAN and felt like it was maybe too much firepower to correct that effect. So yeah, these things were some of the challenges we ran into pushing things past this point. Okay, should I continue now? Okay.
Yes.
So the fastMRI challenges. Yeah, so when we originally released the data set in 2018, I think if you read the paper, you could kind of see the ambition of doing the data set release was something to, we drew a lot of inspiration from ImageNet in the computer vision community. Like we kind of wanted to make the ImageNet for MRI. And when you think about ImageNet, there are two big components. Like one is the ImageNet data set, and the second component is the ImageNet open image recognition competition. So we released the fastMRI data, and then the next thing was like the fastMRI image reconstruction competition. So, so we released the data in November of 2018. And then after people had worked with it for about 7-8 months, we announced a new reconstruction challenge in June of 2019. In September, the challenge actually occurred. We released the data set, we accepted submissions. In December, we published challenge winners and the winners got to present at NeurIPS. And we repeated the whole process in 2020 for brain data. So I'm going to go over both of these challenges here. So as I just mentioned all this stuff about like radiologists valuing images, and it's like hard for metrics to capture tiny changes that are relevant. And the thing is, when you run an open reconstruction challenge, radiologist time is really expensive. So you can't have your radiologist look at all the submissions. There's too many submissions. There's not enough radiologists. So, so because of this, we adopted this kind of imperfect solution for our challenges where we would filter the top 4 submissions in 2019 or the top 3 submissions in 2020. And we did this filtering by SSIN. And then we only had the radiologist evaluate the top participants. So this was definitely imperfect. We weren't entirely happy with this, but it was the only way to process all the data. And so for the 2019 challenge, we had 3 different tracks. So one was a single coil 4X acceleration track. The reason we had a single coil track, so if you're an MRI person, there are really no single coil MRIs. So, but that being said, like multi-coil requires quite a bit of domain MRI expertise, and we wanted lots of people that maybe didn't know anything about MRI to get excited about the challenge. And you really see this in number of submissions. So like 17 different groups submitted to a single coil track. And then the multi-coil is like the real challenge, I guess, which is more relevant to actual practice. So we got 8 submissions for both of these tracks. We had 4 entries in each track that were ranked by 7 radiologists. The radiologists would judge them based on contrast and noise ratio, artifact sharpness, diagnostic confidence, and overall image quality. And we also provide the radiologist with the ground truth. So if you really enhanced your images, like with some fancy adversarial things, and you added stuff that wasn't there anymore, the radiologist would detect that and penalize your submission. Oh, and by the way, these radiologists were recruited from like several different institutions to help try to minimize bias in the evaluation of the results. And so we got some really interesting things. So first of all, I want to show like average rank over here, lower is better. So this just to not confuse you about this graph. And on the x-axis, I'm showing SSIM where higher is better. So what you can see from the 4X track is as SSIM goes up, like for very large differences in SSIM, you can see an improvement in rank. But for very small differences in SSIM, the radiologists were a little bit more discordant. So where this shows up the most is the 4x track. So here, if you look at SSIM, it goes from 0.9265 to 0.928. These are almost all the exact same metric, and the radiologists were extremely discordant for the 4x track. So they were just all over the place. So you see pretty much all the models ranked about the same amount in 4x. And in fact, 2 of them tied. And then for the 8x track, there's a little bit more separation again in SSIM, and you can see maybe a little bit more separation in how the rankings were done. And you can see this even more if you kind of break things down this way. So basically these bar charts are all color coded for how the radiologists ranked each submission. So each one of these bars is a different submission. And if there's more blue, that means more radiologists rank that one the best. And so again, you see for the single core 4x track, there's a lot of agreement on radiologists that one submission was maybe the best. And then there's this really interesting result for the 4x track for this submission that we always highlight is about half the radiologists thought this submission was the best submission, and about half the radiologists thought this submission was the worst submission. So they were kind of all over the place for this one. And then for the 8x track, which when, as I mentioned, there was maybe a little bit more separation in model quality, the radiologists became concordant a little bit more. And so, yeah, this was pretty interesting. And
Matt, I have a question. So you're showing the top 4, and maybe the top 4 are just all essentially equivalent, but I mean, if you actually looked at all of them, would it track SSIM correctly, right? The ranking, the relative ranking.
You mean between all the models submitted to the challenge?
Yeah, like if we just look at the top 4, maybe those top 4 are really essentially equivalent in the multi-coil 4x. So like comparing the 3rd or 4th significant digit of SSIM isn't really meaningful. But if I look at just general trend, then I could still say, hey, this is a good thing to look at.
So I guess my feeling is SSIM is kind of weakly predictive for like once, and keep in mind, these SSIM scores are averages over a distribution. Like if you actually look at the distribution, they're all over the place outside the scale. So these mean values are not really that meaningful. I mean, these models are really all the same from the perspective of SSIM. And I think that's why you see kind of this discordance. And from that perspective, even for these models, like the confidence intervals are quite wide. And I'm actually very surprised that if you have a slightly higher mean SSIM, that this is able to happen. So actually, I think I'm more surprised at how predictive it's been in my experience rather than how useless it is, I guess. So, but that being said, I don't want to make super strong claims about SSIM, but that's just like kind of my own feeling from it.
My question on that, basically just roughly, because I see the differences you have in SSIM are tiny, right? So like the differences on this plot are tiny, like, I mean, at least when we were experimenting, we wouldn't even consider 0.75 and 0.753 to be even different. So would you say that within a resolution of 0.1, SSIM is very predictive of radiologist ranking, roughly speaking?
I think in my experience, you need at least 5 thousandths to maybe get a difference, like 3 to 5 thousandths. Like here you see 3 thousandths. Right. In this case, you need at least a few digits out on the end here for it to start to get predictive. But below that, yeah, I mean, these are pretty much all the same.
Okay.
Yeah, and so this is going to pop up more in the next challenge. So we can go, well, first of all, I want to highlight the winners from the 2019 challenge. So the 4X, as you can imagine, had a tie among radiologist rankings. So two groups had the exact same average radiologist ranking. Philips and LUMC and MSDC are in it. For the 8X, Philips and LUMC won. And then for the 4X single coil, it was a group from the University of Amsterdam. And so after we saw this, we wanted to switch things up a little bit for 2020. So we wanted to make the challenge a little more realistic. So we threw out the single coil track and we only focused on multi-coil. Another round of feedback we got for the first challenge is we didn't look at multiple vendors. We had no idea how well the models would generalize. So we went out and we got a bunch of data from other scanners. So if you're familiar with fastMRI data set, it's all from Siemens MRIs. And so we went out and we got General Electric and Philips MRI scans. And we included that in this new track. And the last thing is we wanted to focus on pathology rather than just impression. So this is kind of, this was a point of disagreement from one of our radiologists. Basically, they said, you know, it's not, radiology is not necessarily like a general image quality. Their training doesn't necessarily point in that. They're trained to look for pathologies. And so you need a more task-oriented image quality evaluation so that they can use their training to assess the image. And this is how those results looked over SSIM. So once again, like, same thing, like there's a lot of clustering for 4X, although this time there was a little bit more separation for the top submission. And there's even more separation for the 8X track. And by the way, the number 7 team here had a weird way they processed the background of the images, and that just killed their SSIM. So that's why you see a drop off on the end of this plot. And then for the transfer track, the interesting thing is a lot of teams had a lot of trouble transferring to the GE data because it had a slightly different pre-processing pipeline. And you know, this is something like they only had the data to work with for about 2 weeks before they had to upload their images, and a few of the teams weren't able to figure out how to negotiate this. The Philips data, which had a pre-processing routine a lot closer to Siemens, was a little bit easier to work with. Yeah, so in this case, the same team on every single track, Airs Medical, it's a startup company from South Korea. So the interesting thing is Airs Medical also participated in the 2019 challenge. And if you look on our public leaderboard, their model from this challenge, I think, is quite a bit better than their model from the 2019 challenge. So they made a lot of improvements. And it was by far the best SSIM in this case. And we saw this in the plots and before we sent things out to radiologists. And so I think we were a little bit surprised to see them get the top ranking so consistently. Yeah, and that's the 2020 challenge result. Any other questions on this before I move on to some ongoing work with undersampled data? Okay. So I kind of, in a way, I've kind of shot myself in the foot with this one because I just spent 40 minutes telling you all that radiologists need to evaluate images, and now I'm going to talk about how to estimate metrics. So, but anyway, I still think estimating metrics is potentially valuable because, like, if you can have a sense of maybe what the ground truth SSIM or like some idea of uncertainty is, you know, you can kind of help inform the radiologist, like maybe what their confidence level should be in an image, or maybe identify, you know, images where there could be systemic problems within a database. So, and the other thing is I'm not the only person to think this. So there's been a ton of work on looking at uncertainty and metrics for rating the quality once you have a deep neural network reconstruction. So, and I'm only listing a partial set right here. So like some of the things you can do is you can do Monte Carlo methods and assume like the residuals are Gaussian in some sense with Stein's unbiased risk estimate to estimate mean squared error. You can do things like bootstrapping where you have a reconstruction and then you essentially compute using some simulations, different realizations, and to try and get a sense of what the spread of the metric is. You can use Bayesian methods like BAEs, Bayesian variational network, to do prior or posterior sampling to get a sense of like how much the reconstructions will vary. And this was a paper I saw recently. I think they just had an error deep neural network. So they got like reconstructions in zero field and they just use that to estimate the error. So I think all this research is very interesting. So for our particular case, what we wanted to do is we wanted to, well, first of all, we need to evaluate error metrics for our model. So which is like the variational network. So, you know, we didn't really have any Bayesian mechanisms to work with there. And we also wanted to be able to kind of estimate metrics with a very simple procedure. So without making too many assumptions on the structure of the residuals. So because of this, the work I'm presenting mostly it expands on this bootstrapping work of Tiger from 2018. where you kind of resample or re-simulate the entire subsampling process. And so if you look at this paper, like the way it works is you have an original image, and then you apply a forward Fourier transform, and you subsample it and do a compressed sensing reconstruction. And then once you have this reconstruction, you try and simulate that entire process again, and you do this several times, and then you can get like a bootstrap estimate of what the error is. And what they observed in this paper was essentially that it looked like this bootstrap error was quite a bit correlated with the actual error of reconstruction, which was kind of interesting. Now, one limitation is they developed this procedure for kind of single coil magnitude images. So it wouldn't apply for our multi-coil reconstruction deep neural network. So basically what I did some work on recently was trying to figure out, is there a way where we could apply this to a multi-coil case? And so what we did is we essentially like tried to apply like a few MRI tricks to re-simulate the forward sampling process. So the main two things we needed is you need sensitivity maps. So to basically expand out a single coil image into multiple channels, and you need phase to like re-simulate the complex phase process. So, and the good thing that kind of helps us quite a bit is that both of these are very smooth, and all our sampling patterns densely sample the central K space. So we get a lot of the frequencies we need to estimate these quantities. So what we do is we take our mass K space and we just take the center part of it. And then for phase, we collapse all the multiple coils down to one coil with an SVD, and then we use that to estimate phase. And then for estimating sensitivity maps, we kind of do something that's standard in the auto-calibrating sensitivity literature, where you just do IFFT and then do sensitivity estimation. So you could also do this with another technique called E-Spirit, but we just did the most simple thing possible to start with. And once you have these, you can run your deep neural network reconstruction, and you can reinsert phase and sensitivity maps, and then forward FFT and add noise, and you get this simulated K-space. And so once you have the simulated K-space, you can rerun the entire pipeline, and you get like a fake ground truth, and you can get these fake reconstructions, and then you can calculate your SSIM and PSNR values. So if you run this procedure, then these SSIM and PSNR values will still be off a little bit. So what we use to do a final correction is we use a little bit of calibration data to fit a scaling and an offset parameter. And then we looked at how it ran on test data. So this is an overall outline of the procedure. So basically you take your model, you compute 5 estimates of your metric, SSIM or PSNR using the Monte Carlo procedure. You fit scaling and offset parameters using validation data, and then you evaluate on the test split. So it's super simple, very easy to do with any model. And the interesting thing is we did a pretty good job of predicting PSNR. So here on the bottom, I'm showing Monte Carlo estimates and the true PSNR value. And this is over a range of acceleration factors from 2 to 20. And you see, like, we generally observe pretty strong correlations between these two. We also observed correlations a little bit weaker, but still present for SSIM. So probably strongest at 2, but keep in mind we're helped a little bit by the upper bound of SSIM. So you can kind of see that, the variance opens up a little bit as you go down away from the maximum value here. But even still, like these values were fairly correlative. And I've also observed in some other work that if you increase the number of parameters you use here, you can get better predictions of SSIM. So just want to note that this is, oh, sorry, someone have a question?
Well, I have some questions, but you can finish it then.
Okay. Yeah, so last thing I want to know is this is just part of a higher study or part of a larger study on high accelerations. There could be other ways to use these Monte Carlo reconstructions. Like you could maybe use the different ones with a neural network, but we just use the simplest approach possible. And you might be able to apply it to new metrics. The main limitation I'll mention is it suffers from the standard drawbacks of linear regression. So if you have outliers in your metrics, it goes all over the place. So I guess one example, ugly wart I'll mention is if you try this with mean squared error, it's a little bit more noisy, but you can calculate mean squared error based on PSNR. So we found that to be a lot more robust than doing the whole procedure on raw mean squared error. So, and that's it for that. So, yeah, so final conclusions. From the interchangeability study, I think the main lesson that we had was humans, especially radiologists, are a critical part of the model optimization pipeline. Reconstructions need to be evaluated for radiologist perception. Takeaways from the challenges are we need to target radiologist interpretation to the task. It seemed like generalization was an open problem with our most recent challenge. And for metrics estimation, incorporating a little bit of physics knowledge can help you generalize other methods for metrics estimation. And that's it. I want to thank everyone, and I can take any questions.
Great, great. Thank you very much for a great talk. Okay, let's open the floor for more questions.
I can start with I had a couple of questions. I didn't understand in this last bit what these A values are. So what exactly is the Monte Carlo portion?
Oh, yeah. So I use R for something else. So A is acceleration.
Okay, so you're basically, and then what are you doing to actually randomize the algorithm? You're just doing different sampling patterns?
Yeah, so these are all regular sampling patterns. So you just change the offset. And so the offset is sampled with replacement. So as you can imagine, for A equals 2, like you can sample the same offset multiple times. But I think I do change the noise realization.
Okay, and then my other question here was, couldn't you generate the phase just from doing a low-res reconstruction with the calibration data instead of doing, because that will give you a smooth phase that's actually probably the same phase as the real image? Or is it that you didn't want to do, is it that you're capturing high frequency phase as well?
No, that sounds like a great idea. Yeah, the thing is, I did this whole thing in 1 week, and it worked well, and I didn't iterate very much on it. But yeah, I think that would work just as well. Yeah.
It would be worth looking at, because you might have high frequency phase that actually the first channel of the SVD captures, but the central region wouldn't. But if it's just fast Fineco data, probably not.
Yeah, I can try it. Yeah, thank you.
That's a cool idea.
Yeah, it worked. I mean, for me, this worked shocking. I did not expect it to work at all. To be honest with you, I expect to be all over the place, and for me to see this was pretty interesting. Considering it's also the most basic approach, I would be interested in maybe extensions that could make this a little bit more robust.
Great. Any other questions?
I was going to ask also, I mean, you're distilling this to a single number, but really you have the distribution of the reconstruction. So you could also look at pixel-wise errors.
Yes. Yeah, and that's actually what was done in the original Bootstrap paper. So I think pixel-wise errors are very interesting. And I guess I'd like to talk to people that have done a little more work in that area, because when we originally looked into doing this, like with VAEs on fastMRI, we proposed this idea, and the feedback we got was like, even if we could do it, there wasn't an obvious path for how to integrate it into the radiologist workflow. And so I'd be interested in hearing more about that from, I know there's lots of people that have done work in this area, so I would be interested to learn what they thought about that.
I guess we have a question from Marius.
Yeah, hi, thanks, Matthew, for the great talk. I was actually curious about something you said earlier. In the knee reconstructions, you said that radiologists often reject methods because they look at the texture, which is not the area where pathologies would occur.
Yeah.
Right. So because you spend countless hours with radiologists, you think it's possible to convince them, if you give them a method that, let's say, guarantees, maybe even theoretically, that the reconstruction in the pathology area is good, but not outside. Would they ever buy that? Because if they're always looking outside, then,
Yeah, I think there'd definitely be people that are open to it. But it's kind of like, I mean, there's also a distribution of radiologists, right? Like some of them are kind of bullish on this technology, and some of them are kind of conservative. So so you have to convince the critical amount, I guess, to change practice on this point. So yeah, I wouldn't close it out. I don't think, I think a lot of them are pretty open-minded. It's just medicine in general is pretty risk averse. So if you present some data that causes some alarm, then then it's hard to get it through.
Thanks.
Very good. Any other last questions?
Can I ask one more question?
Sure.
So you've been working with Facebook for a while, and it seems like you guys have tried lots of different methods.
Mm-hmm.
To what extent do you think, working on MRI reconstruction, is it just a question of let's look at the machine learning literature and try all the things, or is there like really the domain knowledge here has made a difference?
Yeah. You mean for our work?
Well, just this subset of inverse problem work, right? Like we could take all of the new models from NeurIPS and ICML and try them, or is that not the best way to approach this?
Oh, I mean, I think for us, like domain knowledge was everything. Like I wouldn't really feel like we made progress until like, a lot of people like embrace like the domain perspectives of parallel imaging and stuff like that. So yeah, kind of like a lot of my research outlook now is probably colored by that. I think domain knowledge is really important. Yeah, but I also think there's a lot of things to learn from all those NeurIPS papers that maybe we haven't. But then again, I think a lot of people in the MRI community are trying all those things now, and we're learning lots of things. And yeah, I'm always impressed by all the papers I see coming out now that kind of blend between the two worlds. It's kind of fun.
Great. Okay, so let's wrap it up. Thank you very much, Matt, and keep in touch. We will let you know if we have any further updates, and we'll definitely keep an eye out for this great work and any follow-ups. Thank you very much.
Thank you so much, everyone.
Thank you.
Bye.